That one to me, because it's multiplication or division, it's faster.
All right, if I can get everyone back, I'm going to send you back to these problems. And those of you already talking about it, thank you. That's exactly where I wanted you to go. But let me please bring you back. So, do you remember this 7? So this 7, we want our students not to see this just as 7. It is 7. We want them to spot that. But we want them to see it as the 5 and the 2 that it could be, or the 4 and the 3 that it could be. And we have a visual model that we help them with now. It's called a number bond. Those of you in 1st and 2nd grade have probably seen a lot of this. We use number bonds all the way up to 7th and 8th grade. But all it is showing that you can decompose, break up a number. The idea is for kids to develop numerical fluency, being able to play around with numbers. And so 7 can be broken into 5 and 2. It could also be 4 and 3. It can also be 2 and 5, or the other way around. And eventually, this could also be 4.5 and 2.5. So it's really interesting use of it. But we also use it for addition. So for example, when you're adding 7 plus 8, one way of doing it is to break up that 7 into 5 and 2 and use that 2 to add it to the 8. Again, strategy, making 10s. So this problem now becomes, instead of 7 plus 8, 10 plus 5. Is this how we always want our kids to add, even when they're 6th graders? No. We would like them to know 7 plus 8 is 15. But as they're developing this understanding of addition and subtraction, we want them to be able to use a strategy such as making 10s. It is one of the strategies they use. Some kids use a doubling strategy. 7 plus 8 is the same thing as 7 and 7, plus 1 more. 14 and 1, 15. And so this one, here are the numbers, but here's the standard in 2nd grade. The standard still wants them to fluently add within 100, but based on strategies. Strategies using place value. And so by the end of 2nd grade, that vertical format that we're used to is there, but we have one small change that we want the kids to see before they go to the algorithm. Do you notice the change here? There's no carrying, because we want the students to really see that 7 and 8 and that 15, but then when they get to the 2 and the 3, we want them to know it's not 2 and 3, it's 20 and 30. That's the 50. So that's 7 plus 8, that's 20 and 30, 65. And when they develop this partial sums strategy, the next step, the algorithm, makes perfect sense. They are much more, it's much more comprehensible to them. Now, these are the 2 problems I gave you, right? When I give you these 2 problems, without paper and pencil, how is your mind trying to solve it? So I'm going to give you another couple of, maybe a minute or 2 to talk about your strategies, and then I want to have some share-outs. How would you solve the problem on the left or the problem on the right using various strategies? The goal of this, and I'll give you the secret, the goal is you as adults have many strategies embedded in your mind. And when you put that pencil down, you're more likely to actually utilize them. When you pick up that pencil, we are so efficient, we go straight to the algorithm. And there's nothing wrong with that either. Go for it. Talk again. You guys all ready? Yeah. So which one came to you as the easier strategy?
Well, the first one, or this one,
Okay, do you think there's other ways to solve it? If we break up the division to what it really is, which is break it up, how else? If I give a people that bags and you want to put baskets, what's another way you can figure out how many goes in each?
so you feel that you can break what's called, you could break
Raise your hand if you want more time. You want more time? Which one are you trying to get? Are you allowed to do that? you allowed to do it that way? Okay. Smart. How many of you tried the problem on the left? 298 plus 414. Did you guys try that one? All right, if I can get everyone back. Sorry. Good, I'm glad you guys are excited about the strategies. Raise your hand if you want more time. They're too busy talking. That's good. Addition. What strategy did you use?
We add hundreds together, tens together, and ones together.
So you added tens together, ones together. Can you explain what that means?
Yeah, we added 2 with 4 is 6, 9 with 1 it's gonna be 700, and 8 with 4 700.
700. So it's 200, 400, 600, another 100 makes 7. Perfect. Can you explain how you did it?
Yeah, the first number is 2 away from 300. So then I subtracted 2 from the other side and get 12. And then add them together.
Okay, so he noticed 298 is 2 away from 300. Took 2, made 300, and added another 412. Okay? So what we have here already, 2 methods. There's names for both of them. You're using partial sums. You are literally adding the parts together. And you are using incremental adding. You are taking 2 from somewhere because you know it's close, and you can add it that way. They learned these strategies in 2nd and 3rd grade. In addition to moving towards the algorithm, which is the traditional trade 10 ones for a 10, trade 10 tens for 100. They're all equally good. And I used to love saying this to my students. Wait, are you allowed to do it that way? And the look of horror on their face, like they did something wrong. And I said it right here in the division problem. Because the division problem, how many of you did it the standard way? 11 divided by 4 is 2. That's 8. Bring down 3, 32. 4 goes into 32. 8 times 28. How many of you did it that way? Fantastic way. That's the standard algorithm. That's the long division in a short problem. Is there another way of doing it? Raise your hand. How did you do it?
I said there is like, I took up the 12, I said 100 divided by 4 is 25, then 12 divided by 4 is 3, so it's 28.
So she said 100 divided by 4 is 25, 12 divided by 4 is 3, 25 and 3 is 28. That's the same answer. Is that okay?
Yes.
Is she going to be put in math jail for doing it a different way than we've learned? No, this is division. She understands division just like the rest of you did using the algorithm. But when it comes to strategic thinking, that's a really cool strategy. Anyone do it a different way?
Divided by 2, it's 412, divided by 2 is 56, and divided again by 2. 56 divided by 2.
Wait, 112 divided by, you're divided by 2
Yes.
is 56, and then
Another,
divided by 2 again is 28. Wait, that works also. Why does that work?
smaller.
What do you mean?
My brain cannot comprehend that as smaller.
Oh, so, okay. Does that always work?
No.
Does it always work when we're dividing by 4? Yeah, because dividing by 4 is the same thing as dividing in half twice, right? And if you don't believe me, take your paper, divide it in half twice, you get 4 pieces, right? So that's another fantastic strategy. Anyone do it another way? Yes?
Knowing that 4 times 10 is 40,
Uh-huh.
then another 40 is 80, that's 20 times.
Mm-hmm.
And then that gives you 32, that is 8, so it's 28.
There you go. So 4 times 10 is 40. Another 40 is 80, so that's 20. There's 32 left. That's 8 more. By the way, all of these strategies do have names. Partial quotients, friendly numbers. All of these different strategies, kids are learning now. So what we considered fluent before is still fluent with an added component, the thinking component, the conceptual understanding. Let me give you an example. What's 7 times 8?
56.
56. If you paused before you said 56, it's okay. If you don't have it come out of your mouth right away, that's okay. You are still a normal human being and you're good at math. Because for some reason, we make kids feel like if it doesn't come out of your mouth immediately, you are doomed for math for the rest of your life. And that's not true. Not true. If you don't know your multiplication facts, there's a difference between not knowing them and not knowing them automatically. We want that automaticity. What we don't want is kids memorizing and then forgetting them. If they build that automaticity and keep it, fantastic. We want that always. But how do we help them build it? It used to be, the conventional wisdom was memorization. Memorize your multiplication facts. Here's the table. Memorize, memorize, memorize. Test, test, test. Flashcard, flashcard, flashcard. Now that does work for a lot of kids. And then it goes away. And if you don't believe me, I was a 6th grade teacher for 10 years. I had never had a class of 6th graders who all had their multiplication facts automatic. Never. And I had some pretty smart kids. And it wasn't that, oh, those kids that aren't good at math and don't try were the ones who didn't get it. No. It was kids who had been trying every year to memorize those darn facts, and they just couldn't do it for some reason. Now that's still there.
What do you suggest with those kids?
That is a fantastic question. I'm going to lead right to it. Yes, I know. I was there too, and so is my daughter right now. And what do? The focus is build the conceptual as well as practice for automaticity. So let me show you what happens. First of all, this is the standard. It has not gone away. By the end of 3rd grade, students should know from all the products of single-digit numbers. There's more to the standards that says from memory, but we stress to teachers and to parents, from memory doesn't equal memorization. It means automatic. It means it doesn't get in the way of solving problems. So if you say 7 times 8, 56, that's okay. And I'll explain why that's good in a second. But that's the 7th standard. There are 6 standards that come before it that help teachers really get the kids to understand multiplication, because it is a 3rd grade standard. Multiplicative thinking starts in 3rd grade. Can we help 1st and 2nd graders memorize multiplication facts in 1st and 2nd grade? We could. Do they really understand it in 1st and 2nd? Developmental psychologists say no. Some kids, yes, but overall multiplicative thinking comes only when additive thinking has been strengthened and they're ready for this grouping to happen. So most kids who memorize it, they don't really know why 7 times 8 is 56. So how do we build that for them? Here's one way. It's not the only way. Here's one way. These are arrays. Arrays are one of the best ways to help kids see multiplication. Another way is grouping, seeing 8 groups of 7. But an array is 7 groups of 8, and this leads to area later on. But this is a great way to see it. But as you can tell, when you get to your 7s and 8s, those are hard numbers. And in fact, if you ask kids who take those tests, the 7s and 8s are the hardest. 9s are actually a little easier because there's some tricks that go with it. But 7s and 8s are a little bit harder. But what do we do to help kids see it? We let them play with these numbers. Along with learning, we let them see it. And we teach them that decomposing. Remember that 7 didn't have to be a 7? Well, this 7 rows of 8 doesn't have to be 7 rows of 8. It could be 5 rows of 8 and 2 more rows of 8. Now, why would I split it into 5 rows and 2 rows? Those are easier, right? Skip counting by 5s and skip counting by 2s. In fact, if this is later in 3rd grade and in the beginning of 3rd grade they really got comfortable with their 5s, and they know that 5 groups of 8 is 40 and 2 groups of 8 is 16, they can put those together and create that number fact of 56. This child has constructed her own number fact, sees it, has worked with it. 7 times 8 equals 56 has a meaning to it. It's not just a flashcard that I memorized. Now, we develop this thinking a lot in 3rd grade, but we also help them build fluency. Flashcards and time tests, we're trying to get away from that as much as we can, because we've noticed, even though it does work for some kids, it produces a ton of anxiety for most kids. And most adults will even remember back in 3rd grade when the teacher gave that time test. And it didn't matter how amazing you were, as soon as that timer went on, your life became very chaotic, right? And still today, we still have adults who say that, and we still have 3rd graders who say that. We even have 3rd graders who used to think they're amazing in math say, I guess I'm not that good. And that's one of the negative consequences. So how are we doing this? We're doing a lot of games where they have to constantly practice. Just turn over 2 cards and multiply them. Roll dice and multiply them. Find the product. Play a game where they actually have to find the areas of things and shade in areas as they go, they're using multiplication skills, they're practicing, but they're also seeing it come to life. So a little combination of both. How is this helpful? This is helping them understand multiplication. I can go more into that question in a little bit, but I want to move into 4th grade. In 4th grade, first of all, by the end of 3rd grade, they also learn area, and this is a good way of seeing it in 4th grade. In 4th grade, they see this as an area model. This is a model that shows multiplication. And if you're finding the area of a 7 by 8 unit rectangle, can you break it up into 2 smaller rectangles and then put them back together? Yeah. So a 7 by 8 figure is the same as a 5 by 8 and a 2 by 8 put together. Why is this important? Well, I'll show you in just a second. First, please do that problem for me. What is 27 times 38? You don't have to do it mentally, you can pick up your pencil. I purposely gave you a problem that mentally would be kind of tough to do. Not impossible, but tougher. Paper and pencil, go for it. Any method you like. Let me see.
My husband's watching. He's like, what's the they're carrying the one I was confused.
When you're ready, just put your pencil down. Even though there's a possibility that there's multiple strategies being used, I have a feeling, with your pencil picked up, I know the strategy being used. Did most of you put these 2 numbers vertically and use the standard algorithm? Anybody pick up their phone? Good job. Good job. I'm proud of you. It's hard with a group of adults. I have a phone. Why would I multiply these? But if you picked up your pencil, most likely you put the 37 above the 28, even though the 38 above the 27, even though the second one comes next. And you multiplied using the standard algorithm. 8 times 7 is 56, carry the 5. 8 times 2 is 16, and with 5 is 21. And then when you got to that second line, what did you do? Added a 0. Why? Okay? At this point, when I asked my 6th graders, I got a variation of, because you have to. Or my teacher told me. Or that's what you're supposed to do. Some students use it's a placeholder, which is, at least they're talking about place value, hopefully. But the whole concept of now you're multiplying by 10 is not necessarily there. But what's missing even more from the standard algorithm is the idea that multiplication of double-digit numbers requires the distributive property. That's multiplication of 2-digit times even 1-digit. And that's what we really want our 4th graders to learn. For those of you who remember algebra class, this is very similar to multiplying binomials. Do you remember binomials? You'll see them soon. But this is like multiplying binomials. And we want students to understand this relationship. And so we want the students to use place value strategies, because that's what the standard is. In 4th grade, we want teachers to stay away from the algorithm as much as possible, because when students start the algorithm, it becomes a rote procedure. Some of them pick up the conceptual, most of them don't. As a 6th grade teacher, I hardly ever had 6th graders who can explain why. I was glad that they can use it. Fantastic. And that's what we still want. But now we've pushed that standard to 5th grade. We're giving kids 2 years to fully understand multiplication. So in 4th grade, the standard algorithm, we just tell teachers, can you push it off a little bit and use equations, arrays, and area models. Area models is one fantastic way to show it. And if you have a 4th grade child, you've probably seen area models. This is what it looks like. So I want to find the area of a 27 by 38 rectangle. I don't know my 27s. I don't know my 38s. However, I know my 30s and I know my 8s. Right? Because my 30s are just my 3s with a 0 with it. 10 times bigger. I don't know my 27s, unfortunately, so I have my 20s and 7s. Now look carefully at what I just created. I took a rectangle that was one dimension by another dimension, and I made 4 smaller rectangles. This is our tool for trying to help students understand the area model and understand the distributive property. We want students to understand when you're multiplying 38 times 27, you're really multiplying 8 times 7, 8 times 30. 7 times 8, 7 times 30. And if you look at this, you can start to see it. Because now I have 4 rectangles, and for this I'm going to jump up there. To find the area of this rectangle, I need 20 by 30. What would that be? 600, right? Because it's just 2 times 3 and 100 times bigger. 600. How about this one? This is 20 by 8. 160. 7 by 30. 210. And finally this one, 7 by 8. 56. At this point, what should I do with these 4 rectangles? Add them up. Why? Why should I add them up? I want the area of the whole thing, right? Notice none of you said, because you have to. Right? I didn't tell you have to do it. It makes sense. I decomposed it. Now, put them back together. Compose them back together. And if I add them all together, 1,026. Is that correct? Yes. Is that what you got with the standard algorithm? Wonderful. Now, the students are learning this. That's what your calculator said. But that standard algorithm, we still have it. We still have it. It looks like this. Look carefully at that. Why are we not carrying yet? We want the students to see the parts. This strategy is called partial products. Remember partial sums in 2nd grade? Partial products in 4th grade. The kids are seeing the parts that make this up. A 5th grade teacher's job is to go from here to the standard algorithm. It's so much easier to do that when the kids have a year of understanding multiplication, understanding the distributive property. It makes understanding the algorithm much more logical. That 0 that they put makes a lot of sense because we're not multiplying by a 2 anymore, we're multiplying by a 20. It's 10 times larger. That is powerful. But here's the cool thing. It doesn't only help in 4th grade. The benefits of understanding the distributive property keep going. By the way, I have this on a handout for you at the end. You're going to take it with you. You don't have to take the notes on it. If you are, that's okay. But how would you solve this problem? Try it. It's okay if you get the wrong answer. I just want to see how you try it. Don't worry. This is not a test. I will not show your kids. So it's 3 1/2 times 2 1/3. So how do you multiply? That's up to you.
I have 3 times.
Yeah, it's 3 1/2. So we take 3 1/2. Good question. When you are ready, put your pencil down. If your fingers are still working. Now, before I start to show you anything, I'm going to tell you I am still multiplying the same way as if I was multiplying binomials. And you'll see again in a second. Now, when I give this problem to my 6th graders, they're supposed to have learned this in 5th grade. When I give this problem to my 6th graders, how do you think most of them solve it? Well, first of all, half of them don't even try. I don't know. Or Mr. So-and-so didn't teach us this. I'm like, I know that's a lie. I know that's not true. But the ones who try, the ones who do try, this is what they do. 3 times 2 is 6. 1/2 times 1/3 is 1/6. The answer is 6 1/6. And when I tell them they're wrong, they go, then I don't know. Of the students who try, a small percentage of them remember the algorithm. What's the algorithm? What's the most common procedure for solving this correctly?
3 plus 4.
Okay, which one?
So sorry, 3 plus 4.
Oh, that is actually not the way they solve it, but I'm going to come back to that in a second. The way most of my students solve it is convert to improper, 7/2 times 7/3. 7/2 times 7/3. Multiply straight across, rename back to a mixed number, and get your answer. And when I ask them why does that work, I don't know. I have no idea why it works. That's how we were taught. And there's very good reason for why that works. But that's not even the step we want to take. We want the students to eventually learn that algorithm, understanding the conceptual side of it, but we also want them to see the distributive nature of this problem. This is very similar to the 4th grade problem you just saw. And in fact, the standard says, please solve using models and using visual models. Guess which visual model our 5th grade teachers are starting to really like? The area model. And the area model says, separate, decompose these fractions. This is 3 1/2, 2 1/3. I can make that 4-part rectangle again. You want to see it? I will explain. So here's 3 1/2, so we split it down. 2 1/3, split it down. So now we have 4 rectangles. The first one is easy, 2 by 3, 6. This one's a little trickier. This is 2 by 1/2. 2 times 1/2 is 2 halves, or 1. 1/3 times 3, 1/3 times 3, 3/3, or 1. And then at the end, 1/3 times 1/2, 1/6. And at that point, what should we do? Put them back together. 6 plus 1 plus 1 plus 1/6, 8 1/6. Isn't that cool? So this is using the distributive property to understand multiplication of fractions. Do they also learn the other one as well? Yes, but they actually see why it works. Because if you convert this, you will have 7 halves. 7 halves. And you will have 7/3. So in essence, you have 49/6 when you multiply it all together. So that is another way of doing it, but we're still using the visual model. Now, this not only works in 5th grade, it also works here. This is algebra, multiplying binomials. Do you remember how to multiply binomials? Who said FOIL? Somewhere an algebra teacher is either really happy or really upset. Because some algebra teachers taught us FOIL. I was taught FOIL by my algebra teacher. Other algebra teachers hate it because it's just a mnemonic, it's a trick we teach kids to remember. For those of you who don't know, FOIL is first, outer or outside, inside or inner, and then last. So multiply 2x times 3x, because what would most students do at this point? 2x times 3x is 6x squared, 7 times 8 is 56, done. That's not right. What you need to do, this is the distributive property. Do you guys remember the rainbows we drew? Right? We have to remember it's 2x times 3x, 2x times 8, 7 times 3x, 7 times 8. That's how we multiply binomials. Distributive property. FOIL works beautifully here. How about here? It doesn't work anymore. Because first there is, last there is, but inside is jumbled. But if you understood the distributive property, even if you drew those rainbows, you understand multiply everything by everything. You have 2 terms and 3 terms, a binomial and a trinomial. You're multiplying these polynomials together. You have to multiply all the parts. Now, even algebra teachers see the value of using this area model. Because now we have a 2-part and a 3-part multiplied together. Try to visualize what that area model looks like. 2 parts with 3 parts. If you draw the lines, how many rectangles will you have? Not 4. 6. Right? If you have 2 parts, you have 2x and 7 on the left-hand side, and on top you have x squared, 3x, and 8. It looks like this. Prepare yourself, it looks kind of ugly, but it's cool. Do you see it? So now you have all these parts. And you have the 2x cubed and the 6x squared and the 16x. And by the time students get here, they've also learned how to combine like terms. So they know when they put it all together, the 2x cubed stays by itself because it's the only term with a power of 3. But you can put the 7x squared and the 6x squared together. You can put the 21x and the 16x together, and then the 56 is by itself. It's the only constant. Now, I don't expect you to learn this right now. This is what our algebra students are doing. What I really wanted you to see is the similarities. Because I want you guys to imagine this for a second. And I will be the first to admit that this shift in our way of learning math has really made it difficult for our high schoolers because they've been learning a certain way and now we're asking them to shift their minds. We know that's been difficult for them. And if the rollout was different, it would have been made easier. But given what it is, this is where we're going. This is where we've gone, this is where we've had to go. But imagine for a second that this algebra student, 7th, 8th, 9th grade algebra student, depending on progress, let's say 9th grade algebra student. Imagine she had been learning math with these visual models and this conceptual understanding since kindergarten. So here it is. This is her algebra class. She's learning the distributive property with multiplying polynomials. But hopefully this area model is not new to her because she's seen it before. When did she see this? Definitely in 5th grade. But as early as 4th grade, she was using the distributive property to multiply. In fact, in 3rd grade, that's still the distributive property. And it actually is part of the 3rd grade standards. The words distributive property show up in 3rd grade. We don't teach them that vocabulary. They learn the vocabulary in 5th or 6th grade. But this concept, this being able to break it up and multiply the parts together, starts in 3rd grade. But to be able to do that, when do they learn to use the distributive property? I mean, when do they learn to decompose, break things up, play around with numbers? All the way back in kindergarten. Remember those dots I showed you? Told you it's not a trick question? That's the dots. And the students are learning to see numbers and manipulate and play with them. And use this knowledge to understand math strategically. And that's the key. There is no one way to do every problem. There are algorithms. We're not getting rid of them. But we're building to them. And along the building process, kids are able to see strategies. Because what we're finding is, students who are successful in secondary math, they have one thing over their not as successful counterparts. The successful students use math strategically. They have multiple strategies in their minds. And remember that 6th grade example I gave about 7 times 8 is 56? I've literally had students tell me, give me a second. Now in their mind, are they drawing an array and counting one by one? No. But what they're doing is, I forgot 7 times 8, but I know 7 times 7 is 49, 7 more makes 56. To me, that's a fluent student. Because not only did she eventually get her 56 relatively quickly, I would have preferred it to come out faster, but that's still relatively quick, but she knew that she could use a strategy to get there. A student who has memorized 7 times 8 is 56, if they lose it, it's gone. It's gone. And that's when you have students go, I don't know. I don't know. They're not even trying to pull it out of a different strategy. And if they are, they're using rudimentary strategies like 7, 14, 21. They're using really, really early strategies. They haven't developed them. So our goal right now is to help kids develop these strategies throughout the grades. All right? So